1.1 says that a car is moving at a constant velocity. Key phrase, constant velocity. Before we even go any further, what is the consequence of constant velocity? If we have constant velocity, the acceleration is 0, right? And then if we have 0, we know that F net is equals to ma, so the net force is also 0. Right. Which of the following statements about the forces acting on the car is always correct? A says there's a non-zero net force acting on the car. No, the force cannot be non-zero because the acceleration is 0. If the acceleration is 0, the force must also be 0. And then B says the normal force acting on the car is equals to the weight of the car. That is not always true. And then C says there are no forces acting on the car. And D says the net force acting on the car is 0, right? And that's exactly what we said, that when we have a constant velocity, A acceleration is 0, and we know fully well that F net is equals to ma. So we're going to have A multiplied by 0, so F net is 0, right? So our option here is D. 1.2 says the force diagram below shows the forces acting on a box. We have a force applied, we have the normal force pointing up, and then we have gravitational going down. And then it says which of the following equations for the magnitude of the normal force Fn is correct? Our force applied is acting down, right? So let me just have a free body here. So we have the normal, we have the Fg, and then we have the force applied, right? So you can write the force applied like that, or you can do it like this, right? So we have our F applied here, and then nothing is said about the object moving up or down, right? So that tells us that the forces acting on the object along the y-axis are balanced, right? So which forces are acting up? It's only the normal. So the normal is supposed to be equals to Fg plus the y component of F, so that the object is not moving up or down. So we're going to have the normal is equals to F applied, right? Multiplied by, how do we find the y component on a flat surface? We use sine. So sine of theta plus Fg. This is the normal force for this object, and that seems to be option B. So our answer for this question is option B. If the force was acting up, right, we're going to have normal plus F sine theta, right, is equals to Fg, and then the normal would be Fg minus F sine theta. Yeah, usually the question is either the force is acting down or going up, so it's better to know what to do on both cases. And then 1.3 says an object of mass m2 attracts another object mass m1 with the force F. So F is equals to m1 m2 divided by r squared, right? And then we have our gravitational constant. And then now we are told that if the mass m2 is doubled, the force m2 exerted on m1 will be, so we have to find the new force, right? So this is F old, and then now we want F new. And then when we're done with finding F new, how does F new compare with F old, right? So F new will be G, the mass of M2 is doubled, so it will be M1 multiplied by 2M2 divided by R squared, right? So this will be equals to 2 M1 M2 divided by R squared, right? So clearly this is F old. So we're saying that F new is equals to 2F old, which is option number C. So let's go with C there. And then 1.4 says that the velocity versus time graph below presents the movement of an object that is initially projected vertically upward. Ignore the effects of friction. The maximum height that the object reaches above the projection point, the projection point is given by, and then we have a few options. So this is our VI, right? And then our V final is 0, obviously, at maximum height, and the time there is time t. So if you want to find the maximum height, you're gonna use the height is equals to half base times height. You calculate the area of the VT graph, right, all the time. So that will be equals to a half. The breadth is the time, right? So t, and then the height we have v. The breadth is from 0 to t here, right? And then the height is from 0 to v. So we just have a half t multiplied by v, and then that seems to be option A. It says a half vt instead of tv, but then that is still perfectly fine. 1.5 says that a black and red snooker ball are stationary and in contact with each other on a smooth table. A white ball with the same mass m as the other two moves towards the black ball on the line of contact of the black and red balls with a velocity v. It collides elastically with the black ball and stops. So elastically, what does this tell us? This tells us that not only is momentum conserved, but kinetic energy is also conserved, right? So if kinetic energy is conserved, 1 over 2 mv squared before is supposed to be equals to 1 over 2 mv squared after, right? That's what we know about conservation of kinetic energy. So we are told that after the white ball strikes the black ball, it comes to a stop. Okay, let's just underline that. And then now the question is saying the velocity of the three balls directly after the collision will be. The white ball comes to a stop, so we're supposed to have a velocity of 0 for the white ball, right? That's not negotiable. So now the only options that can be true is B and C. A and D are ruled out because the white ball didn't stop for A and D, right? So after the white ball collides with the black ball collides with the red ball, right? And then for the velocities of the red ball, we have a half v here and v. But we know that the white ball was moving at a velocity v, right? So it had a kinetic energy of 1 over 2 mv squared. So we need the red ball to end up with a kinetic energy of 1 over 2 mv squared, right? If we take this value here of 1 over 2 v, we're gonna have, let me write it here, 1 over 2 the mass, and then in place of v we have 1 over 2 v squared, and this will give us 1 over 2 m multiplied by 1 divided by 4 v squared, which will be equals to 1 divided by 8 mv squared. So the kinetic energy will not be conserved anymore if the red ball moves with a velocity of 1 divided by 2v. But then if it moves with a velocity of v, then we'll still have 1 over 2 mv squared. And then EK before will be equals to EK after. So our answer for 1.5 is C. Let's move to 1.6. 1.6 is two boxes X and Y have the same mass. Box X is lifted through a vertical height by a force of magnitude F, and then box Y is pulled up a slope by a force of the same magnitude to reach the same vertical height as shown. And then which statement is correct? A says also we have changing gravitational potential energy of the boxes and the amount of work done by the boxes. So A says the change in the gravitational potential energy of the boxes is the same. So let's look and see if that is true. So for box X, the potential energy will be from 0 to mass multiplied by gravity multiplied by height. And then for box Y, we essentially have the same thing, right? The mass is the same, The gravity is the same and the height is the same. So option A and B are still safe, but C and D cannot be correct because we have different gravitational potential energies for the boxes. Now we have to look at the work. Is the work for box Y more than that of box X, or are the works done the same? Let me erase this so that we can look at what's going on here. So let's calculate the work for box X. So the work for box X will be equals to the force multiplied by the change in position, right? So we just have F multiplied by height, and then let's go to box Y. The force is not the force but the work. The work is equals to the force multiplied by the change in position. The force is applied are said to be the same, right? F. But then the change in position of box Y is the hypotenuse, right? Hypotenuse. And we know that the hypotenuse will always be greater than any of the other two sides of the triangle. So the work done on box Y is more than that done on box X. So 1.6, I'm going with A. And then 1.7 says two identical isolated insulated conducting spheres A and B carry equal charges. They are separated by a distance d and exert a force with magnitude F on each other as shown below. And then a third identical uncharged sphere touches A and is then removed. Okay, so we have F being equals to Q of A plus Q of B. Actually, that is wrong. So we have F being equals to Q1, Q2, and then divided by R squared. Here we have K, obviously. So this is our F old. Now we want an F new, right? Before we find our F new, it is said that sphere C, that is uncharged, touches A, right? So Q new of sphere A and sphere C after they touch will be Q of A plus Q of sphere C divided by 2. But we know that sphere C is uncharged, so it's just Q of A divided by 2. So what we're going to have here, we're going to have F new being equals to K. Let's say Q1 is QA, right? So we're going to have QA divided by 2 multiplied by Q2, everything divided by R squared. So let's write that nicely. So we basically have QA Q2 divided by R squared, everything divided by 2. So our option here for that would be A. Let's look at 1.8. Let's look at 1.8. In the circuit diagram below, X is a variable resistor or rheostat, and Y is a resistor with the fixed resistance. The internal resistance of the battery and the resistance of the wires are negligible, while the voltmeters have a very high resistance. As always, what happens to the readings on voltmeter Vx and Vy respectively if the resistance of resistor X, our rheostat, is increased? So V is equals to I multiplied by R. We are interested on Vx, right? And then we are saying that we increasing the resistance of Vx, right? So since Vx is directly proportional to R, if we increase R, Vx should go up, right? So A, B, C, D, Vx is increasing for option C and option D. So now we have to look at Vy. This one option is saying Vy decreases, and then the other option is saying Vy remains the same. But then it cannot remain the same. That is because Vt is equals to V1 plus V2 and so on, right? So if V is 6 and V1, let's say Vx plus Vy. If Vx goes up, Vy has to go down so that Vt can remain 6, right? If Vy goes up and then if Vx goes up and then Vy remains the same, then the voltage is no longer constant, and we know that the voltage remains constant on an electric circuit. So our option here for C is that it will decrease, right? If you want to go deeper and think about how it's actually going to decrease, that will be because when we increase the resistance on X, right, the current will go down because I is equals to V divided by R. The current went down for resistor Y, right? So Vy is of a less current but same resistance, so the value is supposed to ultimately go down. Let's move to 1.9. 1.9 says choose the option that correctly differentiates between an AC generator and a DC motor. So AC, we talk about slip rings, and then DC, we talk about split rings, and then AC, we talk about mechanical to electrical, and then DC, we talk about DC motor, we talk about electrical to mechanical. Every motor, we talk about electrical to mechanical. Even in AC motor, we're talking about an electrical to mechanical. So A says AC generator converts mechanical to electrical. That is true. And then with the aid of slip rings, that is true. And then for the DC motor, it says electrical to mechanical, which is true. And then it says with the aid of slip rings, which is wrong. So A cannot be the answer. And then B, the AC generator is converting electrical to mechanical. This is wrong. We don't have to look at anything else. And then option C says is converting electrical energy to mechanical. This is also wrong, so we cannot look at it. And then option D says it converts mechanical to electrical with the aid of slip rings. Correct. And then for the DC, it says it converts electrical to mechanical with the aid of split ring commutator. So our option here for 1.9 is D. Let's look at 1.10. The following graph shows 4 different results, W, X, Y, and Z, from an experiment involving the photoelectric effect. And then we have a graph there. So in photoelectric effect, if you have a graph, before you do anything else, derive an equation for that graph, right? So clearly here we have EK max, the maximum kinetic energy, on the Y, and the frequency on the x-axis, right? So that frequency on the x-axis, is it the applied frequency or is it the threshold frequency? Let's derive an equation. We know fully well that the energy is equals to Planck's constant multiplied by the frequency, right? Another way, you can have Planck constant multiplied by the threshold frequency plus EK max, right? So these two here are equal to each other, and that's how we can derive our equation. So we know that EK max is supposed to be our Y, right? So if we rearrange this equation, we're gonna get EK max is equals to H Planck's constant multiplied by the applied frequency minus Planck constant multiplied by the threshold frequency. So if you look at this equation, the applied frequency can be the X and the threshold frequency can be the X. But clearly, if you make the threshold frequency the X minus H, Planck's constant here, will be M, right? So your graph is supposed to slope down, have a negative gradient. But then clearly here, the graph is sloping up. So F is what's on the X, and then the gradient is Planck's constant. Now we have an equation in the form Y is equals to mx plus c, right? So when x is 0, we're gonna be left with minus fo, which is our work function, right? So if we extend this graph here, W will go and pass through the graph, and then X will pass through the graph, and Y will do the same. So W, X, Y, Z, we have different work functions, right? We can only have different work functions if we have different materials. Now let's look at our equation. Which one of the following best describes the four lines on the graph? The lines are for the same material. If you have the same material, you should have the same work function. So same material is not true because we have already established that we have different work functions. And then B is also not true. C and D are the only possible candidates, right? Because it says different materials, all with different threshold frequencies. This is true. If the materials are different, they are most likely to have different threshold frequencies, right? But then as you can see here, the y-intercept of W, X, Y, Z is not the same, right? So they have different frequencies, and that they are different materials. A block of mass 24 kg is on a rough horizontal table. As soon as I read rough horizontal table, I know that there's some frictional force acting on the block, right? And then it goes on to say a force F is applied to the 24 kg block at an angle of 35 degrees to the horizontal. The 24 kg block experiences a force of friction of 7 Newton as it moves. We are even given the frictional force, right? It goes on to say that the block is connected by a light inextensible rope which passes over a light frictionless pulley to another block of mass 12 kg, clearly indicated on the sketch, which hangs vertically as shown in the diagram below. And we are told to ignore the effects of friction, as we always do. And then it goes on to say that the 24 kg block moves to the left at a constant velocity. So the 24 kg block is moving to the left. Let's just indicate that. And then now 2.1 says state Newton's second law of motion. We know that F net is equals to ma, and if we make a the subject of the formula, we get a is equals to F net divided by m. So clearly here, if you apply a F net on an object, the object will accelerate in the direction of the net force with an acceleration that is directly proportional to the applied force and inversely proportional to the mass of an object, clearly. And then you can also say that F net is equals to delta P divided by delta T. That is Newton's second law in terms of momentum. And it will say that the net force acting on an object is equals to the rate of change of momentum of the object. And then now we can move to 2.2. 2.2 says, what is the resultant force acting on the system? If you pay attention to this statement here, it says that the 24 kg block moves to the left at constant velocity. Constant velocity implies that our acceleration is equals to 0. If acceleration is equals to 0 and F net is equals to ma, then F net is equals to 0 newtons. So 2.2 we have 0 Newton. And then now we can move to 2.3. 2.3 says draw a fully labeled free body diagram to all the horizontal forces acting on the 24 kg body, right? So that's our free body diagram there. And then we have the tension as a consequence of the string attached to the 20 kg block, right? And then we also have friction that is going to the right because our object is said to be moving to the left, right? And then our force applied is supposed to be moving to the left, right? So we have force applied here. I'm trying to make the error of the force applied to be equals to the tension plus the friction, right? Because these forces are balancing out. As a consequence, our object is moving at constant velocity or with an acceleration of 0. So now we can go to 2.4. Before we go to 2.4, if you want to support the channel, please check the link on the description there. And then 2.4 is saying calculate the tension in the rope, right? For our 24 kg block, we don't know what the tension is. We know what the friction is, but we also don't know what the force applied is, right? But for our 12 kg block, let's have a free body diagram for our 12 kg block. We have the tension that is pushing up, and then we have the weight that is pushing down, right? And then we know the weight, obviously, because we have the mass. The only unknown variable is the tension. So here, clearly, it will be easier for us to use the 12 kg block to find the tension versus the 24 kg block, right? Because on the 24 kg block, at this point, we have two unknown variables. So for the 2 kg block, so I'm writing 2 kg, we have F net equals to the mass multiplied by the acceleration. So it's just two forces, the weight minus the tension is equals to MA. These two forces are said to be equal, right? So the order really doesn't matter, but usually I start with the bigger force and subtract all the other forces. So what is the weight? The weight is 12 minus 9.8 minus tension being equals to this is 12 kg, not 2, being equals to 12 multiplied by 0, because we know that it's moving at a constant velocity. So we're gonna have minus tension being equals to minus, let me just put that in my calculator real quick. Don't want to embarrass myself, right? So we have 12 multiplied by 9.8, that is 117.6. so our tension is basically 117.6 newtons. It says let's calculate the tension, right? So we can put a direction here. So for the 12 kg block, it will be to the left, right? And then for the 24 kg block, it will be to the right. So let's do 2.5. 2.5 says let's calculate the magnitude of force F. So now if we come back to our free body diagram for the 24 kg block, now this unknown variable of tension, we now have it, right? So we have tension, we have friction, we just need FA. So again, we're gonna say 24 kg, and then we have F net equals to MA, and then force applied, we're saying that is supposed to be equal to the tension plus the friction, right? So it's bigger than those individual forces. So we're gonna have F applied cos of 35 plus minus tension minus friction is equals to MA. Now let's talk about this cos 35. So the force applied is at an angle of 35 degrees to the horizontal, right? We want to resolve it to the x along the x-axis. On a flat surface we use cos, and then on an incline we use sine. Clearly we on a flat surface here, so that's why we're saying FA cos of 35. So it will be FA cos of 35 minus 117.6 our tension, and then minus 7 is equals to 24 multiplied by 0. Why am I saying minus 7? Look here, we are told that the frictional force is 7 Newton, right? So from here, what are we gonna have? We're gonna have FA cos of 35 equals to 24 multiplied by 0 is 0, right? And then we take in minus 117.6 and minus 7 to the right hand side. We're gonna get 124.6. We divide both sides by cos of 35. So 124.6 divided by cos of 35. So I'm getting a force applied here of 146.1343 newtons to the left. We are only actually it's not to the left, it's at an angle of 35 degrees, right? Yeah. Plus even the question only needs us to find the magnitude of force F. So 2.6 says force F is now removed. Does the magnitude of the normal force increase, decrease, or remain the same? So let's find a formula for the normal force so that we can see what happens. So here on our object, when we're talking about the normal force, we now pay attention to the forces acting on the vertical, right? The normal force is pointing up, obviously, and then we have the weight going down, and we have F applied to the Y, right? So clearly from these forces, the normal force is supposed to be equal to the weight plus FAY. So if you remove this force, the normal force goes down. Clearly, the normal force will go down. So here we're gonna have decrease. So let me show you something. It will not always go down when you remove a force. Let's say this force, the force applied was acting up, right? Then we were gonna have the normal force, and then F applied Y, and then down we still have weight. So from this sketch here, we're gonna have the normal plus FAY equals to the weight. So the normal is equals to the weight minus FAY. Clearly in this case, if you remove FAY, the normal would go up. Moons. Neptune's largest moon, Triton, circles its planet in a direction opposite to the planet's rotation. The mass of Triton is 2.139 times 10 to the 22 kgs, and it has a diameter of 2,706 kilometers. And then 3.1 says state Newton's universal gravitational law in words. We know that by formula F is equals to G m1 multiplied by m2 divided by r squared. We can see from the formula here that every body in the universe will attract every other body with a force that is directly proportional to the product of their masses and inversely proportional to the square distance between them. And then now we can go to 3.2. 3.2 says calculate the gravitational acceleration an object will experience on the surface of Triton. So we want the gravitational acceleration. What is the formula of the gravitational acceleration? This is one of those formulas that you will most likely forget, right? But then it is said to be the gravitational acceleration will be equals to G m divided by r squared. This capital letter G being the gravitational constant, and then the mass is the mass of the object of interest, and then r is the radius of that object. In this instance, we're talking about Triton, a moon that is rotating around Neptune. So what do we have here? This will be equals to 6.67 times 10 to the minus 11. That is the value of G. And then the mass of Triton is said to be 2.1390 times 10 to the 22 kg. Now we have to pay our attention to the radius, right? We are told that the diameter of Triton is 2,706 kilometers, but then radius is only half of the diameter, right? So we're gonna have 2,706 divided by 2. We want the radius and not the diameter. But then hold on, the diameter is given to us in kilometers, so it's our job to convert it to meters. So we're gonna multiply this by 1,000. That is because in 1 kilometer we have 1,000 meters. So we're gonna square that, and then let me punch that in my calculator. So we have 6.67 to the minus 11 multiplied by 2.139 to the 22 divided by 2,706 divided by 2 multiplied by 1,000 squared, and that is 0.7794 meters per second squared, right? And then that's about it. We can move forward and go to 3.3. 3.3 says, if the space agency sends a robotic spacecraft of mass 15,000 kg to Triton, calculate the force of attraction when the robotic spacecraft is at a height of 50 kilometers above the surface of Triton. So we know fully well that F, like we have already said, is equals to G m1 m2 divided by r squared. So F will be equals to G, it's our universal gravitational constant, right? Which is 6.67 times 10 to the minus 11. And then we want the force of attraction between Triton and the robotic spacecraft, right? So let's say M1 is the mass of the spacecraft, which is 15,000. And then M2 is the mass of Triton, which let's do question 4. Question 4 says that a ball of mass 50 gram is thrown vertically downwards with a kinetic energy of 2,704 joules from a point P above the ground as shown below. At the same instant, a second identical ball Y is dropped from a point Q, which is located below point P. Ball Y strikes the ground with a velocity of 19.6 meters per second. Both balls hit the ground at the same time. Ignore the effects of friction and take downward direction as positive. Okay, fine. 4.1 says define the term free fall. Free fall is the motion of an object when the only force acting is gravitational force. The motion of an object when the only force acting is gravitational force. And now we can move to 4.2. So we're taking down as positive, right? We are instructed to do so. Usually take up as positive, but hey. 4.2 says calculate the time taken for ball Y to reach the ground. So let's pay our attention to ball Y. We are told that at the same instant, a second identical ball Y is dropped from a point Q. So if it's dropped, we know fully well that VI is equals to 0 meters per second. And then it goes on to say ball Y strikes the ground with a velocity of 19.6 meters per second. So VF is equals to 19.6 meter per second, right? So we have VF, we have VI, we always have acceleration, and we need delta T, right? The time taken to reach the ground. Now the question you ask yourself, which formula has all these four variables? Clearly, that is VF is equals to VI plus a delta T. What is VF? VF is 19.6. The velocity at which it strikes the ground. What is VI? It was dropped. Every time when a ball is dropped, its velocity initial will be 0, and then plus 9.8 because we're taking downward as positive, multiplied by delta T. So basically, we divided both sides by 9.8. 9.8. So 19.6 divided by 9.8, that is 2. So we have delta T being equals to 2 seconds, right? And then that's it for 4.2. Now 4.3 says calculate the speed with which ball X strikes the ground. So let's take our attention to ball X. For ball X, we are asked to find VF, right? The speed at which it strikes the ground. So that's what we're looking for. We can find VI because we are given the kinetic energy, right? So we are told that EK is equals to 2.704 joules. And then VF is our unknown. We have the acceleration, obviously, because we always do. And then we are told that the ball hits the ground, the two balls hit the ground at the same time, right? So we also have delta T. So obviously here we're going to say VF is equals to VI plus a delta T. But before that, we need to determine VI, right? So how are we going to determine VI? We're going to say that EK is equals to half mv squared. And then we know that EK is 2.704, which is equals to half the mass. The mass is 50 divided by 1,000, right? V squared. So dividing both sides by this expression here, we're gonna get 2.704 divided by half, 50 divided by 1,000. And then now we can take the square root on both sides, right? So there we take a square root, here we take a square root, and you will end up getting a velocity of 10.4 meter per second. And then we know that it's supposed to be going down, right? And then so now we have our VI, and we can go on and determine VF. So VF is equals to VI plus a delta T. What is VF? Is our unknown, right? But we know now that VI is 10.4. Acceleration is 9.8 because we're taking down is positive, and the time is 2 seconds. So we basically have 10.4 plus 19.6, which is gonna give you 30 meters per second. So where do we go from here? 30 meters per second down what? We are only interested in the speed, so we don't have to give the direction, but it doesn't hurt doing so. 4.4 says on the same set of axes, sketch the velocity time graph for the entire motion of balls X and Y. So we need velocity time graph. So our velocity is on the Y, and then our time, as usual, it's on our X. So we have velocity here in meters per second, and then we have the time in seconds. Let's pay our attention to ball Y first. Ball Y starts at 0 meters per second when it gets dropped, right? And it goes up to 19.6. So for ball Y, how much time does it take? It takes 2 seconds, right? So we can put 2 here. So ball Y ends up here. So now we can have our VT graph for ball Y. The line is supposed to be straight. And then now let's put our attention to ball X. Ball X starts at 10.4, so somewhere here, right? So it's starting at 10.4, that's the VI, and then it goes up to 30 meters per second, so it's ending up somewhere here. So if we would sketch a graph for ball Y, we'd have something like this. The two lines have to be parallel, right? And then they have to be they have to all be at 2, right? With regards to the time. So that's the VT graph you would get. You will label that this is your X and this is your Y. A box is pushed from rest with a constant applied force of 30 Newton over a horizontal surface which has 3 different regions. Each region is 5 meters long and exerts a different frictional force on the box as it moves through. And then we have a diagram there that clearly demonstrates what the statement is saying. It goes on to say that the graph below shows the kinetic energy of the object as a function of the distance from the starting point as the object experiences the constant applied force of 30 Newton. The first region is from 0 to 5 meters, the second region is from 5 to 10, and the third is from 10 to 15. 5.1 says, state the work energy theorem in words. The work energy theorem essentially says that work net is equals to change in EK. So what this is telling us is that the work net done on an object is equals to the object's change in kinetic energy. The work done on an object is equals to the object's change in kinetic energy. And then now we can move to 5.2. 5.2 says, use the work energy theorem to show that the gradient or slope of the graph represents the net force experienced by the object. I don't really like these questions that have to deal with graphs. But if you're doing physics, they're gonna come and you will need to know them. On the y-axis, we have EK, right? And then on the x-axis, we have the distance. So in work, energy, and power, we have delta EK and we have delta x. So we need to find a relationship where on the y we have delta EK and then on the x we have delta x. From the work energy theorem, right, 5.1 is hinting us on what we need to use. From the work energy theorem, we know that work net is equals to EK, but we also know that the work net is equals to F net multiplied by delta x multiplied by cos of theta, right? So EK is equals to F net multiplied by delta x multiplied by cos of theta. In our situation here, cos of theta, theta will be 0, right? Because you can see the force that is being applied, that is horizontal. So we're going to have delta EK being equals to F net multiplied by delta x. Cos of theta, if theta is 0, that will be 1, right? Because cos of 0 is 1. So we just have delta EK being equals to F net multiplied by delta x. So now we have EK on our y, and then we have F net as our m, right? Our gradient, and then we have the distance as our x. So here clearly the gradient or the slope will be giving us F net. So here you come and say F net will be our gradient, which we're gonna find by saying the change in EK divided by the change in distance or the change in x. Yeah, this is honestly a very strange question. I've never came across anything like this before I came across this question. Anyway, let's move to 5.3. 5.3 says, calculate the net force experienced by the object in the third region between 10 meters and 10 meters. So F net, we know that we're supposed to find delta EK and delta x, right? So we have F net being equals to EK final minus EK initial divided by, so that's divided by x final minus x initial. So that will be equals to, so we want the net force experienced between the region 10 to 15, right? So for x final, we're gonna have 15 minus 10 because that's our initial, right? Now let's find the corresponding EK values at 10. So if this is 2, if this is 4 here, then this is 2, and then this is 6, and this is 8. So 10 is here. So let's go up and see where 10 is. So 10 is somewhere here, and then now let's look at the y-axis and see how the box is and the numbers are pairing up. So if we have 40 and here we have 80, so here we have 60, here we have 20, here we have 100, right? So between we are between 80 and 100. So for EK 1 or EK initial, we have 90, right? Now let's come to EK final. So this is 10, 12, 14, so 15 is somewhere here. So let's go up and then let's see where we end up. We end up at around So this is 160, so this is 180 here. So we have 180. So 180 minus 90, that is 90, right? And then 15 minus 10, that is equals to 5. So 90 divided by 5 is equals to 18, right? So F net between 10 and 15 is 18 newtons. Now let's move forward and do 5.4. 5.4 says, hence determine the magnitude of the force of friction experienced by the block as it moves over the third region. So force of friction. So we know that F net is equals to F1 plus F2 to some Fn, depending on the number of forces you have, right? So on that region, 10 to 15, we know that the F net is 18 Newton, right? So we have force applied minus friction. We're saying minus friction because it opposes the motion, right? So we're going to have 18 being equals to what's F applied? We are told that F applied is 30 Newton. So we have 18 equals to 30 minus Fr. So if we take 30 to the other side, we get minus 12 is equals to minus friction. So this will give us a frictional value of 12 Newton. Then that's 5.4. Let's move to 5.5. 5.5 is saying which region, first, second, or third, offers the largest frictional force. So again, we know that F net is equals to F applied minus Fr, right? One thing, the steeper the slope, the greater the value of F net, right? And then F applied is kept constant. So basically, friction is the one that is determining the steepness of the slope. So where the slope is the steepest, then we have less friction, right? So let's look at our graph here. From 0 to 5, it's pretty much steep, but then from 5 to 10, it's a bit gentle, right? And then 10 to 15 is also very steep. So 5 to 10 is gentle compared to the other parts, right? So there we have the largest friction. So here we're gonna say the second region has the largest friction. I hope you can understand that. And then 5.6 says explain your answer in question 5.5 without any calculation. That's basically what we just did, right? But then another way of doing, we can actually do the calculations, and you're supposed to get a frictional force that is less than that of the region 0 to 5 and the region 10 to 15. In the diagram below, a small metal sphere A on an insulating rod has a charge of minus 80 times 10 to the power minus 9 coulombs. And then 7.1 says describe the term electric field in words, right? An electric field is a region of space in which an electric charge experiences a force. A region in space in which an electric charge experiences a force. Basically, we're saying that E is equals to F divided by Q, right? That's the formula for electric field. A region in space where an electric charge will experience a force. And then 7.2 says calculate the number of electrons sphere A has in excess, right? So the number of electrons a sphere will have in excess will be equals to its charge divided by the charge of an electron, assuming it has a negative charge, right? Because if it has a positive charge, then it doesn't have any electrons in excess. In this instance, we're going to have minus 80 multiplied by 10 to the minus 9 divided by the charge of an electron, which is minus 1.6 times 10 to the minus 19. So I'm getting 5 times 10 to the 11 electrons. So this sphere has 5 times 10 to the 11 electrons in excess. And then we are told now that sphere A is now kept vertically above another sphere B of mass 0.01 kg lying on a horizontal insulated surface. The charge on sphere B is plus 120 times 10 to the minus 9. Sphere A is closely brought closer to sphere B in order to pick it up. Ignore the effects of friction. Okay, and then 7.3 says that draw a diagram that shows the electric field pattern between spheres A and B. So sphere A is negative, let's put it here, and then down here let's have sphere B, which is positive. So the electric field on sphere B, which is positive, will be pointing out, while the electric field on sphere A, which is negative, will be pointing towards itself, right? So let's have something like that. So for sphere A, the electric fields are pointing towards it, and then for sphere B, the electric fields are pointing out, right? And sphere A and B will attract each other. So let's demonstrate that using our electric field lines, right? Yeah, so at the end of the day, you're going to get something like this. If you want to be more precise, sphere B has a greater magnitude compared to sphere A. So you can put more electric field lines pointing out of sphere B, since it has a greater magnitude. And then 7.4 says at a certain height h, sphere B is just lifted off the surface due to its attraction to sphere A. Just lifted off, right? Let's note that, just lifted off. And then draw a free body diagram showing all the forces acting on sphere B at this instance. So let's talk about the key word just in this statement, right? So if it is just lifted off, then that tells us that the force that is lifting it off and the force that are keeping it down, they are very close to each other. They are approximately equal. So that's why it is just lifted off for a split of a second, right? So let's look at sphere B and do some analysis. So if sphere B is being lifted off, it's gonna be lifted off by the attraction from sphere A, right? So let's have an arrow pointing up here and demonstrate that this is FA on B, and then what's keeping it down is gravity, right? Because it is said to have a mass of 0.01 kg. So let's have FG here. So we need these two lines to be approximately equal to each other because the sphere was just lifted off. And then 7.5 says calculate the height h in the diagram at this instance, right? So we definitely gonna use the free body diagram of sphere B, right? Because that's the only information we have. So we're gonna say that FA on B is equals to FG. So FA on B will be K Q1 Q2 divided by R squared, and Fg will be the mass multiplied by the gravity. So what is the value of K? We know fully well that K is 9 times 10 to the 9. The charge on Q1, let's say Q1 is A, that will be 80 multiplied by 10 to the minus 9. Don't forget, we're only interested on the magnitude of the charges and not the direction. And then for B, we're going to have 120 times 10 to the minus 9, and then we divide everything by R squared. So R in this instance is H, right? So we're going to have H squared, which is equals to the mass 0.01. Gravity is 9,8, right? So now we're basically solving for h squared. So if we cross multiply, h squared is going to be multiplied with 0.01 multiplied by 9,8, right? And then we're going to end up dividing both sides by 0.01 multiplied by 9,8. So we're going to have h squared being equals to 9 times 10 to the 9 multiplied by 80 times 10 to the minus 9 multiplied by 120 times 10 to the minus 9. And then this we are going to divide it by 0.01 multiplied by 9,8. So now we can take square roots on both sides, right? So we'll say h squared to the power 1 divided by 2 is equals to this entire expression to the power 1 divided by 2. So h will be equals to 0.0297 meters, right? And then let's move to 7.6. And now we are told that sphere A is now placed on the horizontal insulated surface a distance x from sphere B as shown in the diagram below. P is a point between A and B, which is 0.05 meters from B. The magnitude of the net electric field intensity at point P as a result of the presence of sphere A and B is 54.45 times 10 to the 4 nano per coulomb. And then 7.6 say draw a labeled vector diagram indicating the directions of the electric field at point P as a result of spheres A and B. So point P is a point charge, right? So we always assume that it's positive. And then sphere B is positive, right? And then sphere A is negative. So how do point P and sphere B interact? They repel each other, right? That means that the vector of charge B on P will point in that direction. And then how does sphere A and sphere P and point charge P interact? They attract each other. So A on P will be in that direction also. This will be electric field due to B, and this will be the electric field due to A. And let's move to 7.7. 7.7 says calculate the distance x between spheres A and B. So we are given the net electric field and the magnitude of the charges, right? And the distance between the point charge and one charge. So it should be obvious to see that we're going to use E net is equals to EB plus EA, right? So E net is 54.45 times 10 to the power of 4. And then the electric field due to B will be K. I won't substitute anything for K for the sake of space, right? And then the magnitude of B is 120 times 10 to the minus 9 divided by R squared, the distance between P and B, which is 0.05 squared. And then plus K again for the sake of space, the magnitude of A, 80 multiplied by 10 to the minus 9 divided by R squared. So R squared here will be the distance between A and P, right? Let's just put Y there. So let's put Y squared, right? So we're looking for X. You can see that X will be Y plus 0.05, right? So after we found Y, we basically have X. So if we do that, we can take this expression here to the left hand side, right? So we're going to have 54.45 multiplied by 10 to the power 4 minus 9 times 10 to the power 9. I'm substituting K now, multiplied by 120 times 10 to the minus 9 divided by 0.05 squared. And then this will be equals to 9 times 10 to the power of 9 multiplied by 80 times 10 to the minus 9 divided by y squared, right? So now I can rearrange this equation in attempt to find y squared. So basically, if you have a is equals to b divided by y and you want to find y, you're going to cross multiply, get ay is equals to b, so y will be b divided by c. You can see that b on our equation is this expression here, and then a on our equation is this entire expression, right? So let's rearrange it so that we can find y ultimately. So we're gonna have y squared is equals to 9 times 10 to the power of 9 multiplied by 80 times 10 to the minus 9 divided by this entire expression. So that's essentially what we're doing there. And then after this, we will take square roots on both sides. So we have y squared to the power half, and then this entire expression to the power half. And then if you do that, you're gonna get y is equals to 0.08 meters, right? So x will be 0.08 plus 0.05, which is 0.13 meters. 8.1 says define the term EM of a battery. That is maximum energy provided by a battery per unit charge passing through it. Maximum energy provided by a battery per unit charge passing through it, right? And then now we can go to 8.2. 8.2 says calculate the reading on ammeter A1. So now what we have to do, we have to analyze our circuit before we answer any questions. Clearly, this is the positive terminal and this is the negative terminal. Current flows from the positive to the negative, but then it cannot bypass here. It has to take the long road, right? So our current is flowing just like how I'm indicating on our sketch, right? Here at this point it spills because we have resistors in parallel. So here on this question we are told that switch S is now closed, right? Which is situated here, and then the ammeter reading on A2 is 0.3 amps, right? So here on A2 we have 0.3 A, and then it goes on to say that the reading on V2 is 6.8 volts. Now we can attempt to answer our question. You will realize that A1 is in series relative to the second, right? So A1 is going to read I total. So what this question is asking us is basically to find I total, the total current. On this path here, after the current split, right, we have a current of 0.3 A, right? And then what we can do is to find the current that this 20 ohm resistor is going to experience, right? Then the sum of those two will be equals to I total, because the current is only split in here. A portion will go up and then another portion will go to the 30 ohm resistor. From our definitions, we know that in parallel, the current is different, but the voltage is the same, right? So we can say Vp is equals to I multiplied by R. So we're going to calculate Vp using the 30 ohm resistor, right? That is because we have the current and the value of that resistor. So that will be 0.3 multiplied by 30, which is going to be 9 volts. So now we know that the voltage that the 20 ohm resistor is going to experience will be 9 volts, right? And then the value of the resistance is 20 ohms. So now we can calculate the current on that line, right? So here what I wrote here is for the 30 ohm resistor. Now we take our attention to the 20 ohm resistor. So we're gonna say again Vp is equals to I multiplied by R. We already know Vp from the 30 ohm resistor, right? So that will be 9 being equals to I multiplied by 20. So the current will be equals to 9 divided by 20, which is equals to 0.45. Now we know that I total will be equals to 0.3 plus 0.45, which is equals to 0.75 amps. And then now we can move to 8.3. So for 8.3, we are asked to calculate the total external resistance of the circuit, right? Resistance total is always equals to the resistance in series plus the resistance in parallel. So which resistors are in series and which resistors are in parallel? The 30 ohm resistor is in parallel with the 20 ohm resistor, right? And then X is the resistance that is in series relative to the circuit, right? So let's start with the resistors in parallel. So we're gonna say Rp is equals to R1 multiplied by R2 divided by R1 plus R2, right? This formula works. You can also do it using 1 divided by Rp is equals to 1 divided by R1 plus 1 divided by R2 and so on. That formula will perfectly work. So here for R1, let's take 20 ohm as R1. So we're going to have 20 multiplied by 30 divided by 20 plus 30. And then if you put that in your calculator, you are going to get 12 ohms, right? So we are done with our resistance in parallel. Now we have to move our attention to our resistance in series. So let's come to resistor X. For resistor X, we know that, so let me just denote here that we're talking about X. We know that it's going to experience IT because it is in series relative to the circuit, and that will be 0.75A is what we calculated in 8.2. And then we know that the voltage is said to be 6.8 volts. So now calculating that resistance becomes pretty much straightforward. So we're gonna have V equals to I multiplied by R. So the resistance will be equals to the voltage divided by the current, right? What's the voltage? The voltage is 6.8 and the current is 0.75. And then when you put that in your calculator, you get 9.06 ohm. So that will be our RS, right? So now we can say R total is equals to RS, which is 9.06 plus RP, which is 12. So 9.06 plus 12 will give you 21.06 ohm. So our resistance total is 21.06 ohm. And then from there we have 8.4, which says calculate the internal resistance R of the circuit, right? The current is the same everywhere in the circuit, right? On the resistors, on the external resistors, and even on the internal resistors, in the internal resistor. So that is why EMF is equals to I, which is the current, multiplied by the external resistance plus the internal resistance. What's the value of the EMF? Is given to us as 18 volts. And then what's the current? We know fully well that the current is 0.75. And then what's the external resistance? That is 21.06 plus R, right? So now what we can do, we can divide both sides by 0.75. So 0.75 and 0.75 cancel out. Now we are left with 21.06 is equals to 18 divided by 0.75. This we have plus R here, we have plus R, I'm making a mistake. So that is 21.06 plus R is equals to 18 divided by 0.75. Now we can make R the subject of the formula, right? We're gonna get the internal resistance being equals to 18 divided by 0.75 minus 21.06. And then if I put that in my calculator, I'm getting the internal resistance to be 2.93 ohms. And then we can move ahead to 8.5. 8.5 is saying resistor X is now replaced with another resistor with a lower resistance. How will the reading on voltmeter V1 be affected by this change, right? So let's go look at V1. V1 is connected across the battery, right? If the current is flowing to external resistors and we have a voltmeter connected across the battery, that voltmeter will read V external. If there's no current flowing to external resistors, then it will read EMF. But then here clearly we have the 20 ohm, the 30 ohm, and resistor X when switch S is closed, right? So our voltmeter V1 will definitely read V external. But we know fully well that V external is equals to current total multiplied by resistance external. So now resistor X is replaced with another resistor of lower resistance, right? So what's going to happen to resistance external? Resistance external will go down, right? It will go down. So clearly here, when resistance total goes down, V external will also go down. And then we are asked what the reading of the voltmeter will be, right? The change will be decreased, because clearly when resistance external go down, voltage external goes down. And then 8.6 says we should explain our answer in question 8.5 without any calculation. There's something I didn't say when I was explaining the decrease, right? But then now I'm going to touch on it. Maybe the question you're asking yourself is that when the resistance decrease, don't the current increase? That V external will stay the same, right? Because we know that the current is equals to V divided by R. So if we say in R decrease, then why shouldn't the current increase? And then nothing happens to V external. But then the thing is, EMF is constant, right? And then EMF is equals to IR plus I multiplied by internal resistance. So we're saying the external resistance will go down, right? When the external resistance go down, the current will definitely go up, right? But then let's look at this part of the equation here. R stayed the same, and now the current went up, and we need EMF to be constant. So there's no way for V external to increase or stay the same. It has to decrease so that the EMF remains a constant. So even though the external resistance is decreasing, the current will not go up such that V external stays the same or goes up. A simple sketch of a generator is shown below, and then 9.1 says the north and south poles of the magnet remains unchanged. If the coil is rotated in the direction S shown in the sketch, will the induced current flow in the direction as indicated? Answer yes or no. So basically what they're asking us is asking us to determine the direction of the induced current, right? First of all, let's note how the coil is being rotated. The coil is being rotated anti-clockwise, right? And then here is our north pole and here is our south. So with our index finger, we're going to point from the north to the south. Here we are applying Fleming's right hand rule, right? And then after you do that, you're going to pick one side of the coil. Either you're going to pick AB or you're going to pick CD, right? When you're rotating the coil anti-clockwise, CD is going up, right? And then AB is going down. So with your thumb, you decide which side you are taking. If you take CD, then your thumb must face up and your index finger should go from north to south. Let's take CD. So if you take CD, here you're going to have your thumb pointing up. If your index is going from north to south and your thumb is pointing up, and then you turn your middle finger 90 degrees relative to your index, then your middle finger will be pointing from C to D. Let me just use a better pen there. It will be pointing from C to D, right? So the induced current that is given to us on this sketch, right, is not true. So the answer here should be no. It's very difficult to indicate the right hand rule or the left hand rule when I'm making videos like this, but I'll put some notes on the description so that you can see how it works and see why I'm saying the answer is no. And then let's move to 9.2. 9.2 says, is the output voltage AC or DC? The output voltage will definitely be AC. Now, why do we say that? We say that because of the presence of slip rings and not split rings, right? We're saying that because of the presence of slip rings and carbon brushes, right? So it's AC because we have slip rings. And then let's go to 9.3. 9.3 says, what will happen to the output voltage if the coil is rotated faster? So the output voltage when the coil is rotated faster is going to go up, right? So the answer here would be increase. And then another way you can use if you wanna increase the output voltage is to use magnets that are more powerful, right? Or basically increase the strength of the magnetic field, right? And then now we can go to 9.4. 9.4 says, what is the position of the coil relative to the magnetic field when the output voltage is a maximum? That position would be parallel, right? Because when it's perpendicular, that's when voltage is 0, and then when it's parallel, the voltage is maximum. And then we can go to 9.5, which I've been waiting for this entire time. We sort of are using electrodynamics and electrostatics at the same time, right? So here we're told that lights in a household are connected in parallel as shown in the simplified circuit below. So lights or any other appliances, they work as resistors, right? That's just something I want you to note. So we are told that we have two large bulbs rated 100 watts and 220 volts, and then we have another one 60 watts 220 volt 2 respectively connected to an AC source of RMS 220 volts, and then the fuse in the circuit can only allow a maximum of 10 amps, right? And then let's ignore the resistance of the conducting wires. 9.5.1. So 9.5.1 says, calculate the peak voltage of the source. So what is peak voltage of the source? Peak voltage of the source is Vmax, right? And then this 220 volts that we have here is our VRMS, right? Root mean square voltage. So we're gonna have VRMS equals to Vmax divided by square root of 2. So what is our VRMS? Our VRMS is 220, which is equals to Vmax divided by square root of 2. So our Vmax will be equals to, we're multiplying 220 by the square root of 2. So if you do that, I'm getting 311.13 volts, right? I hope you're getting the same thing. And then for 9.5.2, it says calculate the resistance of the 100 watt light bulb when operating at optimal conditions. So let's go to the 100 watt bulb and look at the information we have so that we can answer our question, right? It's rated 100 watt. So we already know that the power average will be equals to 100 watts. What else do we know? We know that it needs 220 volts, right? Because that's given on the rating. So here we're going to have VRMS being equals to 220 volts. And now what are we looking for? We're looking for the resistance, right? So what is the resistance? When you're working with electrodynamics, instead of having let's say V equals to I multiplied by R, you instead have V RMS and I RMS, and you're gonna use VRMS and IRMS when you're calculating power 2. Right, let me just erase this and we carry on. So now we're gonna have power average equals to VRMS multiplied by resistance squared, right? The only difference is that now we have VRMS instead of just V that we were already using. So now we're gonna have the power average being equals to VRMS squared divided by R, which we're already using in electric circuits, but then instead of VRMS we just had V. So what is the power average? The power average is 100, and then the VRMS is 220, and then we square it and we divide by the resistance. So the resistance will be 220 squared divided by 100. So let me just punch that in my calculator real quick and see what I get. So that is 220 squared divided by 100 is giving me a value of 484 ohms, right? And yeah, I think that's all. We can move to 9.5.35 marks. So we're bound to do some work here, but is it really? Let's see what happens. So 9.5.3 is saying the 60 watt light bulb is now removed and replaced by an electric ion. Okay. An ion generally consumes more power than a bulb, right? Yeah, and then it goes on to say with a power rating of 2220 watts. Makes sense, it's an ion. We are replacing a bulb. Explain with the aid of a calculation why this is not advisable. Yeah, so now what I'm thinking is this ion has a power rating of 220. So for ion, let's just jot down some information for the ion. For the ion, we have a power of 2200 watts, right? And then the ion will experience a voltage of 220 volts, right? Because it will be parallel to the 100 watt bulb, which is receiving 220 volts, because our power source can only give us 220 volts, right? So we have the power, we have the voltage, we can determine the resistance, right? The resistance, and then we can determine the current. What would the resistance help us with? If we determine the resistance, then we can calculate IT, right? The total current. But then another way of which you can calculate the total current is if we just use the power and the voltage, right? So let's say that the power is equals to VRMS multiplied by IRMS. So our IRMS will be equals to the power, which is 2200 divided by 220, and this will be equals to 10 amps. So on this line here that I'm circling now in yellow, Let me just make that, more appealing. So on that line there, we're going to have 10 amps, right? But then we also have this line here, which will have its own current. We can actually calculate that current actually, because we know the power there and we know the voltage. So, okay, fine. Current of the 60 watt battery will be equals to the power divided by 220. So let me just put that in my calculator real quick and see what we get. Where's my calculator? Okay. So we have 60 divided by 220, which is equals to 0.27. So 0.27. And then the fuse can only allow a current of 10 amps. But now we are requiring a current of 10.27. So what's going to happen? The fuse is going to burn out because the current that is required is greater than that which the fuse will let pass through, right? So it will not be advisable at all to have this electric ion on this circuit of ours. An experiment is conducted to investigate the relationship between the wavelength of light incident on a metal and the maximum kinetic energy of the emitted electrons from the surface of the metal. This experiment is conducted for 3 different metals, namely iron, copper, and gold. And then 10.1 says, state in words what the photoelectric effect is, for 2 marks. That's just basically the definition of photoelectric effect, right? Which says that it is the process whereby electrons are ejected from a metal surface when light of a suitable frequency is incident on the metal surface. It's the process whereby electrons are ejected from a metal surface when light of a suitable frequency is incident on the metal surface. And then 10.2 says, write down the name of the physical quantity or quantities represented by the gradient of the graphs, right? So now what we have to do here is to find an equation for this graph, right? We know that the energy is equals to the Planck constant multiplied by the frequency. But we also know that this energy can be equals to the work function plus EK, right? So these 2 things that I'm circling are equals to each other. So in our graph here, we have 1 divided by wavelength as our X and the maximum kinetic energy as our Y. So in this formula that we have here, we have to make the maximum kinetic energy the subject of the formula. So we're gonna have EK, this is EK max, right? EK max being equals to H multiplied by F minus the work function. But we know fully well that on our graph, we have 1 divided by wavelength, right? We can say that the frequency is equals to the speed of light divided by the wavelength, right? So that is equals to C multiplied by 1 divided by wavelength. So in our equation, we can now say that EK max is equals to H multiplied by C multiplied by 1 divided by wavelength minus the work function. So now you can see that this will be your Y, and then this here is going to be your M, and 1 divided by wavelength is going to be your X, and then minus work function is going to be your C. So we have Y equals to mx plus C. We are interested on the gradient of the graph, right? So we can now tell that the gradient of the graph is the Planck's constant and the speed of light, right? So you can see H and C, and then you get your 2 marks. And now we can go to 10.3. 10.3 says that which of the 3 metals needs incident light with the largest frequency for photoelectrons to be emitted? Give a reason for the answer. We have already said that the frequency is equals to the speed of light divided by the wavelength, which you can also write as the frequency being equals to the speed of light multiplied by 1 divided by wavelength. So we basically multiplying these two numbers, right? So the bigger 1 divided by wavelength, then the more frequency is required. So when we go to our graph here, which one is the bigger value for 1 divided by wavelength? Clearly is gold, because it's here, right? It has a value of between 2 and 1.5. So here the metal that will require the largest frequency for photoelectrons to be emitted is going to be gold, right? Why are we saying gold? We're saying gold because the frequency is equals to the speed of light divided by the wavelength, and clearly gold has the highest value of 1 divided by wavelength, right? And then now we can move to 10.4. 10.4 says the symbol X in the above graph represents the work function of ion. They don't even have to tell us, right? We can already tell because we have this equation here. And then it goes on to say that if the work function for ion is 9.945 times 10 to the minus 34 joules, calculate the maximum velocity of an emitted electron from the surface of ion if the wavelength of the incident light is 9 times 10 to the minus 11 meters. So again, we have the energy being equals to H multiplied by F being equals to the work function plus EK max. So here we are asked to find the velocity of an emitted electron, right? So EK max will be equals to 1 divided by 2 mv squared, because that's the equation for kinetic energy, right? So now we have H multiplied by F being equals to the work function plus 1 divided by 2 mv squared. So what we're looking for here is this V, right? So let's try and make V the subject of the formula. So we can take this term here to the left hand side. If we do that, we're gonna get H multiplied by F minus the work function is equals to half mv squared. So now we can divide everything by half m and take the square root, right? So we're gonna find that our V is supposed to be H multiplied by F minus the work function divided by half m, and then everything to the power 1 divided by 2. So now it's just a matter of substituting our values in V equals to this expression here, and then we get the maximum velocity of the emitted electron. So let's go ahead and do that. So here we're going to have the value of H is a constant, that is 6.67 times 10 to the minus 34, and then what is the frequency? Let me look here. We don't have the frequency, right? But we have 1 divided by wavelength, which is somewhere around here, just before 0.5, right? So let's estimate that value to be 0.4 because we're not really sure what it is. So here we can have multiplied by the speed of light, which is 3 multiplied by 10 to the power 8 divided by 0.4 times 10 to the minus 8. Where is the minus 8 coming from? Look here where I'm circling in yellow, right? Is multiplied by 10 to the minus 8 meters to the minus 1. So now we have that. So let's go ahead and subtract the work function, right? We are told that the work function is 9.945 times 10 to the minus 34. And then there we have it. Now we're supposed to divide everything by half m, right? So let me just, so we're going to have half the mass of an electron, which is 9.11 times 10 to the minus 31. Yeah, I think that is correct. And then everything to the power of 1 divided by 2. So V is going to be equals to, let me just put that in my calculator real quick. So I'm getting 10.48 times 10 to the 7 meter per second, right?